All right, well, greetings, everybody. We are going to try our darndest to still make progress, even though Mr. Hudeberg is not currently present. But in this video, we're going to talk about Bohr diagrams. We're going to talk about what valence electrons are. So we will define that term, valence electron. Right? And we'll learn how to identify the number of valence electrons in an atom. And we will also then learn how to use the idea of Bohr diagrams and valence electrons to do what are called Lewis dot diagrams. All right, so a Bohr diagram. Now I've shown you guys these already, so this is not new information to us. But a Bohr diagram is just a model of an atom. We talked about how that's not really what atoms look like, but it is an instructive way to draw atoms nonetheless, because it does help us understand a little more about electrons, particularly valence electrons. All right. So a Bohr diagram is drawn just like you see it there on the left-hand side, which is an example of a Bohr diagram for iron. All right. Typically, you just write the element symbol in the middle, although you might, rather than writing the element symbol, you might write something like iron, 26 protons and 30 neutrons or something like that if you wanted to. But typically just a circle showing the nucleus, element symbol in the middle to help people know which element it is we're talking about is fine. Now, one of the things we want to start paying attention to is that each element symbol does get a circle, right? And that circle sort of indicates an energy level, or in this case, it's sort of like a solar system model, so it's like an orbit around that nucleus. But again, electrons don't orbit in the same way planets do around a star, okay? It's just a helpful model for us. All right, now each of these little dots on the circle represents an electron. So all these electrons that we assign down here in our electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6, they're all of those electrons are in fact depicted on this Bohr model, right? So those two electrons right there are these two right here, right? That first circle outside the nucleus represents that energy level 1. Those are those two electrons. Now, energy level 2, we have the two s electrons here and the two p electrons, right? All 6 plus 2, 8 of those are going to be found on that second circle. So there's the two s electrons, right? And then here's the 6, 1, 4, 2, 4, 6 p electrons there. The 8 in the third energy level, these guys right there are found on the third circle, right? Now, the 4 s electrons, so our fourth energy level is represented with this fourth ring right here. Now, notice, though, that in our fourth energy level, we only have 2 electrons, right? And those are those 2 in the 4s. That's those 2 right here, 1 and 2. Right? But as we learned in our electron configurations, after we fill the 4s sublevel, then it's almost like we drop back down to start occupying that d sublevel. So these 6 electrons, which don't fill up that d sublevel, by the way, are shown in red on this diagram. So there's 1, 2, 3, 4, 5, 6. There's those 6 d electrons shown in there. Notice that they're not on that fourth ring. They belong on the third ring because they have that little 3 in front of them. All right? Now, when they share an orbital, we tend to pair electrons, so that's why the little s electrons in blue are paired up, right? Once we get enough electrons in the piece, then we pair them up and stuff like that. We'll talk about that in a little bit. All right, so let's do a little practice. Okay, let's do one for phosphorus, right? Phosphorus we can find right here. It is number 15 on our periodic table, right? Now, what we're going to do is we're just going to go ahead and write a little P right in the center and draw a circle around it to indicate that the number of protons in that nucleus makes this phosphorus. There would actually be 15 protons there, as we know, right? Now, let's do a quick check. How many rings do I need to draw around my phosphorus nucleus? Well, that's pretty easy to tell from our periodic table, right? So let's just count our rows. This is row 1 up here with hydrogen and helium. Row 2 is lithium through neon. Phosphorus is in fact in row 3. So all I'm going to do Let's draw 3 additional circles around phosphorus. 1, 2, and Mr. Huderberg does not draw the best circles, but you guys get the idea, and 3. All right, now I need to go in and take the 15 electrons that we would find in a neutral atom of phosphorus and assign them to their correct energy level, right? So energy level 1, right here, in row 1, just has 1, 2 electrons. So in the first circle, I'm just going to go ahead and go 1. Whoops. Excuse me. Just going to go 1. Make them nice and big there for you. I apologize I can't go a second color, but my computer software is not behaving today, right? So those 2 dots right there. I'm just going to kind of like shade this in a little bit just to indicate that this is a nucleus that we're talking about, and that's not a ring right there. So the 2 electrons in energy level 1, right? That'd be my 1s2. Those 2 electrons are shown in that first ring. Now we don't have to write an electron configuration to do a Bohr diagram. I'm just illustrating. Okay. Now energy level 2 has 2s1, 2, 2p6, right? So there's 1, 2, 3, 4, 5, 6, 7, 8 electrons, right? So typically what I'm going to do just to sort of illustrate is I'm going to go 1 right there, 2, 3, 4, and spread them out as much as I can, right? Then I'm going to come back and pair them up. 5, 6, 7, 8, right? So that second ring is all the electrons on the second energy level. So that would contain both the 2s2 electrons and the 2p6 electrons. So the 6 there plus the 2 there makes 8. Those are both in energy level 2, second ring. Now, last one, we got phosphorus is in row 3. So our final ring, we're only going to need to worry about drawing 1, 2, 3, 4, 5 electrons on it. So I'm just going to go like this. 1, 2, 3, 4, and then I'll pair up just 1, right? So kind of like we're doing Hund's rule here, trying to spread our electrons out as much as we can. So what we show here is 15 electrons. There's 2 there. 8 there makes 10, and then 5 on that outer ring makes 15. All right? The reason we only have 5 on the outer ring is phosphorus only has 5 in energy level 3, right? Because it's got the 2 from the 3s, and then it's a 3p3. 2 plus 3 makes 5. Okay, so that is a Bohr diagram for phosphorus. Now we can do the same thing for potassium, right? Draw a little K, a little circle around the K, and then again I'm going to kind of shade that in just so we don't get confused thinking that that's an orbital. That's our nucleus, right? Now, potassium is way over here at number 19, okay? But potassium is in fact in row 4, right? So I'm going to quickly draw 1, 2, this is messy, 3, and 4 circles around our potassium. Oh my gosh, that is horrible circles. We're going to pretend those are circles, right? And then again, we know that our first energy level just has 2 electrons. We'll go ahead and put those in there. We already know that our second energy level is all the way filled up with 8 electrons. So I'm going to draw all 8 there. 2, 3, 4, 5, 6, 7, and 8. All right, my third ring, my third energy level, it's all filled up, right, with 8 electrons. My S and P is filled up, excuse me. Oops. 1, 2, 3, 4, 5, 6, 7, and 8. I'll try to make those a little darker for us. All right, now I'm in row 4 is where potassium is, right? It's in that row. It's only got 1 electron on that 4th energy level, right? So I'm just going to put it over here. right? Actually, it doesn't matter if you start on top or start on the left side, right side, or bottom. We just want to show that potassium only has that one electron in that outer level, and the rest of those are filled up. Okay? So we're not going to have you guys do giant Bohr diagrams because it just gets really messy. It's kind of a pain, right? And ultimately, the electrons we actually care about, as we're about to learn, are the ones on that last energy level anyway. So let's go over here to what are called valence electrons. So valence electrons are the electrons that occupy the outermost energy level, right? So if we go back to our Bohr diagrams, we're talking about the electrons on the outer ring. All right, those are our valence electrons. Right? So in the case of calcium, right here, so our outermost energy level, if we don't have a diagram, right? Notice that energy level 4 is the last energy level, right? So we would just be talking about those 2 electrons right there in the outermost energy level. All right. Now, the number of valence electrons an atom will have ranges from 1 valence electron up to 8. So we're never going to have less than 1 in a neutral atom. We'll never have more than 8 in a neutral atom. All right. Now, the reason we care about these valence electrons is the reactivity of an element. So what an element will react with is determined by how many valence electrons it has. All right. And as we learned a little while ago, right, if they're in the same chemical group, right, or column on the periodic table, right, similar, right, those elements tend to be similar in terms of the way they behave chemically, right? And that is in fact because they have the same number of valence electrons being in the same group. All right, so how do we identify the number of valence electrons? Well, it's pretty simple. If we have a periodic table in front of us, which we almost always will, right, all we care about looking at is what group we're in. Okay, so it's just like this. Group 1 has 1 valence electron, so hydrogen, and lithium, and sodium, potassium, all of those have 1 valence electron. Everything in group 2, beryllium, magnesium, calcium, strontium, barium, radium, all of those have 2 valence electrons. Now, notice, right, that we're going to skip over this D block, right? We're just going to say that all of these also have 2, all the way from groups 3 through 12, right? Because remember, after we go to 4s, we drop down to 3d, so these are not in the outermost energy level. We have 2 for all of these up to zinc, but we don't start adding in more to that 4th energy level until we get back to the p sublevel. So starting at group 13, all of these have 3. Everything in group 14 has 4, 5, 6, 7, and then I'm going to put the 8 there above the neon because helium, again, is sort of an oddball, also just has 2 valence electrons, just like it's only the S sublevel, not the P. It's sort of an oddball. All right, so again, how do you tell how many valence electrons an element has based on the periodic table? You just look at the group that it's in, right? If it's in group 1, they have 1. Group 2 has 2, right? We're going to carry that 2 all the way across the transition metals, though, until we get to our P subblock. Then it's 3, 4, 5, 6, 7, 8. So how many valence electrons does bromine have? 7, right? Because it's in that second to last group. How many does argon have? 8. How many does aluminum have? 3. How many does rubidium have? 1. Okay, super simple. All right, now moving ahead. How do we identify the number of valence electrons for electron configuration? Pretty simple. We just look for our highest energy level. Here, that would be 3 in this case, right? So that means we would have 2 plus 4, so this would have 6 valence electrons. All right. Now looking at this next element, let's see, our highest energy level is actually 4, there and there. So we're only going to worry about those 2 there and those 2 there. We're not going to worry about those 10 because that's energy level 3. So we're just going to say this element has 4 valence electrons. All right. Now, if we have a Bohr diagram, it's really simple. You just count how many are in the outer ring. Boom, 2. All right, that's all I got for you guys today. Boom. Take this information, use it as a weapon on the next Chem Quest.